So the next speaker is Andrew Schultz, and he will talk about Galois module structure of square power classes in biquadratic extensions. Please go ahead.
Great, thank you very much. And of course, thanks to all the organizers for putting together this conference. It's different from how it usually is, but it's nevertheless amazing and something I look forward to every year. I also want to send a special thanks to Claude. Claude, I'm glad that you're here. Claude, you'll have seen most of this talk already because this is a topic that I've been working on for a little while, and you invited me to a conference in Hawaii last year. And actually at that conference, I spent a lot of time thinking about how I could take the result that I presented there and perhaps streamline it. And I'm pretty convinced that it was being on the islands of Hawaii that made the difference so that I could actually tighten up this result. So I've talked to my department chair to see if they can send me out there more frequently to improve the quality of my research. And that's pending, so we'll see how that goes. But in any event, all right, so I'll be talking about thinking about power classes, square power classes for biquadratic extensions as Galois modules. The work that I'm going to be presenting today is in collaboration with a handful of people. John Swallow and Frank Commodi actually started this project a long time ago. And Jan Minach and I have more recently picked it up and sort of rephrased the perspective a little bit and actually been able to tighten down the decomposition in a couple of different ways. Frank is actually out of the math business now. You can see that he is in the piano business, it turns out. And John Swallow is still in mathematics, but he's on the administration side. He's now the president of Carthage College. So, and Jan is himself. This is him exploring the fields of mathematics as effort. All right, so motivation and background. This is sort of some big picture ideas that are going to get us to the topics that I'll be talking about today. The big thing that is motivating a lot of what we're thinking about is the inverse Galois problem, which says if I give you a field K and a group G, is it possible for us to describe or ideally even parameterize all of the extensions of K whose Galois group is G? So these are the things I'm calling G extensions. Of course, this is a very big problem that is very much open. But in some simple cases, we have some really nice answers. So for example, if the group G that you're interested in is the group Z mod PZ, the cyclic group that has P many elements in it, then depending on the shape of your field, there are nice parameterizations. So for example, if the characteristic of your field is not P, and if your field has a primitive Pth root of unity, Kummer theory says that you can parameterize, in fact, all elementary P abelian extensions of K, so not just the ZP ones, but the direct sum of Z mod P ones. And you can parameterize them as vector subspaces of the P power classes. In the case of characteristic P, there is a related notion called Artin-Schreier theory. There's a slightly different object that parameterizes these elementary P abelian extensions. So in either of these two cases, you can sort of think that there is a single object that is doing the parameterizing for us. And it's giving us sort of a nice correspondence between vector space language and these particular extensions. The case that I'm not talking about here, when characteristic isn't P, but there aren't Pth roots of unity, it turns out that there's a nice parameterizing space in that case as well. So really, no matter what, you can always find a nice parameterizing space for elementary P abelian extensions. So the big idea is that if you take this vector space structure and you put more structure on it, then perhaps not surprisingly, you get back more Galois theoretic information. So in particular, if your extension K is, if you take your field K, and if that field K is an extension of another field F, then the Galois group of K over F acts naturally on this parameterizing space. And that means that the parameterizing space can become a module. And then the idea is that it is the submodules of the parameterizing space that correspond to the elementary P abelian extensions of K that are now additionally Galois over F. Okay, so if we put this module theoretic structure on them, we wind up picking up more information. And in fact, it turns out that you can even compute the Galois group of the corresponding extension in terms of basically module theoretic information plus a little bit of field theoretic information. So the sort of idea that I have here is that if you take the structure of the parameterizing space, and if you can allow that to communicate with sort of module decomposition information and maybe a little bit of a dictionary between how modules and groups relate to each other, then you wind up picking up a lot of information for this extension K over F, all right? So a number of results have been computed that allow us to calculate certain Galois modules in exactly this situation. So for example, when the Galois group of K over F is a cyclic P group, and you consider the parameterizing space for elementary p abelian extensions, we know the module decomposition precisely, and we know the dictionary between module theoretic information and field theoretic information and Galois groups. And so we sort of know the picture all the way there. It turns out that a more recent result investigates not just pth power classes, but p to the sth power classes. So you can think of this as sort of a finer understanding of what's happening. And it turns out then, when you again look at cyclic p extensions, and assuming that your characteristic is in p, the module in that case has been decomposed as well. You get a really nice looking module. There are a handful of other results that have been computed just to give you a flavor of these things. Pth power classes are the first cohomology group, and you can generalize that to higher cohomology group. And when you do that, it turns out you can compute modules in that case as well. And if you really want to get fancy, then you can make a connection between cohomology groups and looking at Milnor K groups for the field. We've done that at least in the case where characteristic is P, so that's sort of where there's a breakdown between this correspondence. But it turns out that the decompositions that have been done in the cohomological case rely on this connection, the sort of Bloch-Kato connection between cohomology and these Milnor K groups. So again, the short version of this is that lots of modules have been computed at this point. What's common about all these decompositions? Well, the sort of thread that runs through all of them is that when you look at these decompositions and you look at the indecomposable types that show up in these decompositions, you get far fewer isomorphism types of indecomposable modules than you would expect. And from the Galois theoretic point of view, what that means is the modules are somehow simpler than you would expect, and that is forcing us to have an interpretation that the corresponding absolute Galois groups are somehow more interesting than a random pro-P group would be. So the idea here is that we can take these ideas and sort of parlay it into the language of absolute Galois groups, and that tells us that these maximal pro-P Galois groups basically are not random pro-P groups. So just to give you a sense of what that might look like specifically, this is a result that I presented when I was in Maine a handful of years ago. So I'm going to write nu of g comma f to denote the number of extensions of f that have Galois group G. Of course, I'm living inside some fixed algebraic closure here. And there is a relationship that you can carve out between the number of extensions of a field f that have a handful of different possible Galois groups. So this HP cubed is the Heisenberg group of order p cubed. MP cubed is the other non-abelian group of order p cubed. And the idea is that you can count the number of times that this group shows up over a field f in terms of the number of Heisenberg extensions that you get for that field, the number of pth power classes for that field, and then what I'm calling the number of non-embeddable ZP extensions of f. What this really means is the number of ZP extensions of f that don't themselves live inside of a Z mod p squared extension. So you're not allowed to go from this cyclic thing to a higher cyclic thing, essentially. So again, the idea of this corollary, I'm not so interested in exploring what it means precisely, other than to say that the module decompositions that we've been able to calculate so far put a lot of restrictions on the information that we get about Galois groups occurring over a given base field. All right. But everything that we've done up to this point has been in the cyclic case. So what about in the non-cyclic case? How can we sort of get started on that? The natural answer is you should probably let G be the simplest group you can imagine that's not a cyclic group. And the simplest non-cyclic group, of course, is Z2 plus Z2. So this is why we're thinking about biquadratic extensions. It's the easiest thing that we can next try to tackle. So what we're going to do is we're going to think about square power classes over biquadratic extensions. So this is basically what the picture looks like. In a biquadratic extension, of course, you get to that extension by adjoining two square roots. That gives us a lattice of intermediate fields. There are dual Galois elements corresponding to each one of the generators of this particular field. The Galois group is just the direct sum of those two things. We'll use a convenient shorthand. We'll call the intermediate fields K1, K2, and K3. When we look at square power classes, I will at least do my best to write brackets around a square power class, as opposed to the element itself, which has no brackets. And there will be times where it's convenient for us to not only think about square power classes over K, but to think about square power classes over these intermediate fields. And so when we do that, we change the bracket to have a subscript of an I to remind us of the field that we're thinking about. All right, so as we proceed, there are going to be some sort of cartoon diagrams that I draw. And all these diagrams are basically just convenient ways to draw a picture instead of writing out some horrific system of linear equations. So there are basically 4 different kinds of arrows that are going to show up. There are going to be arrows that point south and west. This means an application of the operator 1 plus sigma 2. So alpha to the 1 plus sigma 2, this just means alpha times sigma 2's action on alpha. Arrows that point to the southeast, this is an application of 1 plus sigma 1. And when arrows bend like this, what we're trying to indicate is that those 2 actions on a given element result in the same value, okay? So really there's only 1 plus sigma 1 and 1 plus sigma 2 floating around, but when they agree, we'll sort of bend them so that they line up with each other. So this is sort of a convenient way to draw some pictures. And I mentioned before that the theme that runs through a lot of these module decompositions is that the modules that we wind up getting back are far more stratified than you would expect. The number of indecomposable isomorphism types that appear is really, really small relative to the number of things that could appear. So for example, in general, if you're looking at a module over a biquadratic, over a Klein-4 group, it turns out that there are 2 families of indecomposable modules that are odd dimension. They're called omega minus n and omega to the n power. And each of them corresponds to these sort of long chains that either run like this or run in the opposite direction. So again, right from the get-go here, you can see that in the case that we're thinking about, if you were to pick up a random module over this particular group ring, and you thought about what kind of isomorphism classes of indecomposable modules could appear, well, there are an infinite number of things that could arise at this point, right? There are lots of different things that could show up. These omegas give us a class of ones that are odd dimensional. There are some other ones that are finite dimensional and very nice. So these correspond to various quotients of the group. So for instance, you could take G and quotient out by nothing, and then you would get a free module. So that means that there are no extra relations. Or you could take a module and you could quotient out by a particular action so that you only pick up, for example, this half of the diagram and these 2 pieces disappear. So that's sort of what's happening in this diagram, and so on and so forth. So there are a handful of sort of simpler ones that show up as well. All right. What module decomposition were we able to calculate? Here's what we're able to do. So in the setup that I've mentioned, characteristic is in 2 and the Galois group is the Klein-4 group. It turns out that when you look at square power classes, you only wind up getting back a handful of things. Whoops, I see I have a typo here. I somehow always seem to have typos in my talks, but now I can actually write over the screen, which is good. So what do we get? We get a direct sum of things that look like omega 1. So those are some 3-dimensional summands. We get a bunch of things that look like these quotient ones that I showed you on the last slide. And then you get this weird one that's called X. And X takes on one of a handful of different possible values. It can be a direct sum of some omega minus 1s, or it can be an omega minus 2, or it might be a direct sum of some trivial things. But the point here is, again, when we look at this module, remember, in general, when we look at a module over this particular kind of group ring, there are an infinite number of indecomposable types that in theory could arise. And if you run through the possibilities here, you can count on 2 hands the number of isomorphism types that appear. So not only are we getting a way of describing all the ones that could appear, but from the infinite number of possibilities that show up, we get less than 10 things that could show up across all possible fields, right? This isn't even just for a specific field. This is over all possible things. We only get a handful of different kinds of things that can show up. So this is sort of falling in line with things that we've seen before, but in some sense is more exaggerated than the kinds of results that we've seen because it's so sparse relative to what could show up. I want to give you a quick sketch of a proof here. Yesterday in this session, Hester Graves, who is a Wellesley alum, mentioned that since we're giving talks remotely, that all rules go out the window and we can do whatever is appropriate for this new context. And for her, that meant that she's allowed to talk about a proof. I remember when I was first trying to learn how to give talks, I went to an AMS meeting and I saw one amazing talk. I don't remember who it was. And in the talk, the person said, in a good talk, you never talk about proofs. And I thought to myself, okay, don't talk about proofs. And then I went to another talk, which is an amazing talk. And in that talk, the person said, a good talk always gives a proof. And I said, oh, okay, it always gives a proof. And I didn't know what to do because they were so contradictory. I just assume what this means is that a good talk has to talk about what a good talk talks about. So I feel like I've done that now. I'm going to go ahead and sketch a proof. The big idea here is that when you look at submodules inside of a particular module of this kind, it turns out that those two modules have trivial intersection only when their fixed parts have trivial intersection. And so for us, what we're going to do is the following. We're going to focus on the fixed part of our particular module. And the good news is, basic Galois theory gives you a big hint about what that fixed part probably looks mostly like, right? Because what does the Galois group mostly fix? Well, for the field, it only fixes F. So we know that F plays a big role in the fixed part for this particular module. The question is going to be, what else is there, right? So here's what we're going to do. First, we're going to build a big module whose fixed part is exactly F. Then what we're going to try to understand is, what does a complement of F look like inside of the fixed module? What is the plus that we're looking here? And how can we build a module over that? And finally, once we've done those two things, hopefully what's going to happen is those two modules that we pick up are independent from each other and span the entire space. So here we go. We're going to build over F. The strategy for us is going to be, for a given element in F, we're going to try to maximize the number of pre-images it has while minimizing the number of generators. So for example, it could be that F, this element here, is at the bottom of a free module. And in that case, how many pre-images does it have? It has all three of these pre-images, right? And the number of generators is 1. This is the best we can possibly do, all right? So that's optimal. That's kind of our first choice. What's next? Well, next would be to have, instead of 3 pre-images, to have 2 pre-images. That might, of course, mean having more than one generator, and that's fine. So this is the thing we're going to call B. All the F's that satisfy a diagram look like this, we're going to call this space B. And then you could have F being in the pre-image of exactly one thing, and we'll call those things C, D, and E, because there are different ways that can happen. F can show up on the southeast side or the southwest side, or it can somehow be this like glued double version that shows up here. So what we do is we take F and we basically split it up into these various subspaces. The nicest of the subspaces is this fancy A. Inside of A is this nicer, or this still pretty nice B. And then sort of B winds up being the intersection of these various other petals, C, D, and E. So for example, if you intersect C and D, it's not too hard to show that that intersection is exactly B. But the same thing is true for any other pair of these two things that you wind up picking up, all right? So we sort of build over this particular module. That's the nice thing. That's the thing that's built over Y. All right, and when you do that, what you wind up getting back is a submodule that is expressible as a direct sum of a bunch of free things and some omega-1 things. So in the big decomposition we've seen, that's where these pieces are coming from. Next up, we have to fill out the rest of the fixed part. And to answer how we fill out the rest of the fixed part, we're going to answer the proverbial question of WTF, which in this context mean whether 'tis F. Do we have an element that is inside of F, or is it not inside of F? And you can answer that in a lot of ways. Kummer theory, for example, gives you a way to answer whether an element is represented by something in the ground field just by looking at the Galois group that you get by taking the biquadratic extension and adjoining the square root of your element gamma to that. But it turns out there's a more convenient way to do this using norm maps. And it turns out that this happens precisely when your element gamma is in the intersection of the kernel of a bunch of norm maps. So in the next slide, I create a function T, and it's going to map from the fixed part into a bunch of these classes in intermediate fields. And the idea basically is that F is exactly the kernel of this map. So what we're going to try to do is basically try to find a big pre-image for the image of this map that trivially intersects the kernel of this map, which is F. And what we wind up getting back, turns out it depends on the image of T. For example, if there is an element that has the property that the kernel of T does not swallow up all of this particular space, whatever this thing is, then it turns out that means that there is an element X that is simultaneously a norm from K down to K1 and a norm from K down to K2, but of course also fixed. So we get norms in each direction and a fixed element. If that's true, you can make an argument that these two elements also have non-trivial images in this direction, and T of all of these things, this thing, this thing, and this thing, are all sort of independent from each other. They span a three-dimensional space. So this is one of the cases we get. I see I have a minute left. This is how we get the omega minus 2 module that shows up. Let me skip over the next example, but that's how you generate an omega minus 1. And what we pick up is a sort of different range of possibilities for what this X summand is, depending on what the image of T winds up looking like. So in the last minute, let me just mention here that when we put all this stuff together, basically the game that we have to play is to make sure they're independent. And that works because their fixed parts are independent. And then what we do is we run through a bunch of cases to argue that depending on the module structure that gamma has, we can argue that the element lives in the particular thing. So I won't have time to talk about this, but the module could be any number of things. And in each of those cases, we pick up different pictures, and those different pictures tell us what to do. Obviously, I'm too ambitious for what a 20-minute talk can look like. Thanks, everybody, for your attention.